Good afternoon, everybody. I would like to present the first part of this webinar. I will share the screen in order to present my slides. Perhaps you can see now the slides. I don't know, before the invitation. Well, we can explain the main aspects of the partial discharge measurements for monitoring purposes in substations. Well, the webinar is split in 6 points. I will concentrate my presentation in the first 3 points, and my colleagues, Javier Ortega, will explain the other 3 points, the last 3 points. Well, we can start speaking about partial discharge. What is a partial discharge? As you probably know, the most part of the people know that a partial discharge is a localized electrical discharge that only partially depletes the insulation between conductors, between 2 conductors. As you can see on the right in this figure, you can see 2 conductors. Could be, for instance, the conductor of a cable and the screen of the cable. And between the conductor, there is a solid insulation, and perhaps in the solid insulation, you have a small defect. For instance, a void. In this void can appear a discharge. Discharge is a pulse, current pulse, is a current pulse. And this current pulse is very small, is around several milliamperes for several nanoseconds. As you know, the charge is the integral of the current pulse. For this, in conclusion, the integral of a current pulse of milliamps, that the duration is several nanoseconds, the charge is around picocoulombs. Milliamps multiplied by nanoseconds involves picocoulombs. It's a small pulse, it's a small pulse with a small charge that can be measured. How to do it? How to do it? There are 2 alternatives. We can measure the radiated energy, or we can measure the conducted energy of this pulse. For instance, in a GIS, we can have different kinds of partial discharge sources. For instance, we can have a protrusion in the high voltage conductor, or perhaps we can have a protrusion in the grounding of the envelope enclosure of the GIS. We can have also another kind of PD sources. For instance, free moving particles due to the assembling process. They can appear this kind of particles. Or we can have also dirty in a insulation surface. In this case, we have a partial discharge surface, partial discharge. Or perhaps we can have an electrode that is not connected to high voltage and is not connected to the grounding. In this case, it's a floating electrode that can appear also partial discharge. In any case, we have pulses, small pulses that can be measured in a radiated waveform, for instance, with antennas. We can use antennas in order to measure the radiated energy provoked by these pulses. But we have another alternative. We have the alternative to measure the conducted current, the conducted pulse. How? Well, the pulse is conducted through the conductors connected to the high voltage side, and also the pulse can flow through the capacitance. The pulse is looking for the capacitance that appear in the network, for instance, in the underground cables. the underground cables, the cables have a significant capacitance, and in this, through this capacitance can flow the small PD pulses. And this is the way to measure the conducted partial discharge pulses. Well, in cables we have other kind of PD pulses, but for instance, the most important, of course, in cables is the internal cavity. Is a void, is an internal defect that is the most critical situation because provoke a continuous degradation of the insulation. But at the same time, we can have different other PD sources. For instance, corona. This is typical. Corona in the air. They are in all substations. Probably we have corona, especially with the voltage is very high. And this partial discharge, corona partial discharge, doesn't provoke any critical aspect in general. Of course, we can have also external surface partial discharge that in the insulations, in the insulators, for instance, we have dirty pollution, and in the insulations, and we can have this kind of PD sources. But in general, these PD sources are not critical because the most critical is the void. And of course, also we can have floating electrodes that can provoke partial discharge. In any case, we can measure the partial discharge through the cable sheets. The cable sheets, the screen of the cable, flow in the cable sheet flows the partial discharge pulses, and in this part of the connection to the earth, the connection of the cable sheet, the screen, the connection with the earth, we have a good opportunity to measure partial discharge pulses using a special sensor that are high frequency current transformers. In this slide, you can see a cable connected to a GIS and connected to an overhead line. In this cable, for instance, we can have a partial discharge in a middle position, and it's very interesting to analyze what is the best position to have more sensitivity. And you can see the equivalent circuit. The equivalent circuit is shown below, and in this circuit you can see the defect provokes two currents pulses, one on the right and the other on the left. The sensor can place on the right in the position of the cable screen, the connection of the cable screen to the earth in both sides. But as you can see, if you use the sensor placed on the right, the current through the sensor is lower because the capacitance through this capacitance is the overhang line capacitance, and the overhang line capacitance is smaller than the cable capacitance. If we use the sensor placed on the left, we have more opportunity, more sensitivity, because the current through the sensor is the current through the capacitance on the right of the substation. It means that it involves other cables, other elements that have significant capacitance more than an overhang line. For this reason, in this case, the situation, the location of the sensor is very important in order to have more sensitivity. In this case, the best selection, the best choosing will be is to place the sensor on the right of the termination of the cable, for instance. This is a good placement. Well, you can see different PD sources can appear, but the most important for us in a cable is the internal PD corresponding to a cavity or a void in the insulation, cable insulation. In a transformer, well, in a transformer is a complex machine, and we have many different kind of PD sources. We can have PD sources in the bushing. In the bushing can appear corona, inert, surface, partial discharge, cavity in the dry insulator. We have also possibilities to appear partial discharge inside of the transformer, in the windings, or inside of the tank. And there are probably possibilities to have cavities, bubbles, surface on oil, free particles at floating. We have many different possibilities in the transformer. The transformer, as you know, is the insulation in the transformer is oil and is papers, and this kind of insulation is not too critical because it can appear significant partial discharge levels before the breakdown. For the reason we have more opportunities to detect and defect and to prevent the failure in a transformer. We have more time to make a decision, the final decision. Well, in any case, it's important to ratify that partial discharge means that we have to measure with an environment noise that is important. It's important. For this reason, the classical partial discharge measurements carried out in the laboratories is not easy to do it in on-site measurements because the noise is very significant. And in general, for on-site measurements, we use sensors that we can place invasive or non-invasive. We can use both alternatives. Well, our solution is basically thinking in both alternatives, but the most important for both alternatives is that if you use sensor, non-invasive sensor, in this case, probably the noise is more significant and we have to use more important tools to remove the noise. For the reason, the technical specification, IEEE technical specification 62478 appeared in the last years in order to solve the on-site problems, in order to give several concepts to measure in online, in on-site high voltage installations. And the blue box technology that is patented is in the line, is in the direction is of this standard in order to give a solution according with this standard with the noise is significant. How is working the blue box technology? How is it working? Well, the blue box technology is focused in high frequency measurements. High frequency measurements involves significant noise problems, and for the reason we need the important mathematical tools in order to remove the noise. And the problem in online monitoring is that the noise can change. One day we have a type of noise and another day we have another kind of noise. And for the reason, we need an automatic tool in order to remove the noise automatically. And this is the basis, conceptual basis of this technology. How it works? Well, it's on the basis of the Wallet transform plus several mathematical algorithms, statistical algorithms in order to carry out the automatic measurements removing the noise. The Wallet transform can identify pulses and can separate, discriminate noise from the pulses. Okay, well, for the reason, the blue box technology have the opportunity to remove the noise automatically with not any adjustment of any setting of the instrument, partial discharge instrument. We don't need to choose any measuring frequency. We don't need to choose any trigger level. It's totally automatic because the method consists to measure in all bands between several hundred of kilohertz, several hundred to kilohertz to 25 megahertz. In these bands width, we measure all signals, noise and pulses. And we use a mathematical tool in order to remove the noise and to obtain only pulses. What are pulses? Corresponding to the data, raw data. And we can, in this way, we can identify small PD pulses behind the noise. On the, you can see in this slide, a green area that is the noise, and you can, we can automatically identify small PD pulses behind the noise because we analyze by the Welle transform the pulses that are included in the noise. As you can see, we can have small pulses superimposed in a modulated noise, exactly in the last, in the bottom figure. We can see a small pulses just in the crossing zero level that is identified automatically by the Babbelet transform using the blue box technology. And for this reason, we can identify automatically the pulses of the APD source, corresponding of APD source. For instance, in this case, a cavity is identified automatically, removing the noise. Well, this technology is especially prepared for high frequency measurements. And of course, this kind of measurements can be used to detect partial discharge in any equipment of the substation. It means in the transformer, in the GIS, or in the cable. In a substation, we have any kind of equipment, and we can measure the partial discharge through the cables connected to the transformer using high frequency current sensors. Well, we can, sorry. Well, in order to clarify these ideas, we have developed in a European project a specific testing setup in order to analyze the capabilities of the PD measuring instruments to remove the noise. This testing setup is composed by different test cells and can provoke a specific partial discharge sources, pulses. For instance, cavity, surface, corona, or floating partial discharge. And we can measure the PD pulses through a high frequency current transformer, but at the same time, we can measure the PD pulses through a measuring impedance. In this circuit, we can measure the pulses, but at the same time, we can control a superimposed noise generated by a generator, arbitrary wave-shape generator. And we can mix both signals, the PD pulses plus the noise. And in this way, we can identify what is the capability of the PD instrument under qualification. Because we can modify the noise in different levels in order to verify if the instrument can identify the partial discharge. I have a small presentation in order to show these ideas. Here you can see a a PD pattern that is generated and is measured in different measuring instruments. On the left is a conventional, conventional is an instrument based in measure in a frequency, in a middle central frequency of measurement, measuring central frequency. For instance, in this case, is working in 300 kilohertz with a bandwidth of 250 kilohertz. As you can see in this case, there is not any noise signal. Sorry, but now we can mix this PD pulse, this PD source with a noise. You can see here the noise in the time domain and the noise in the frequency domain. And you can see this noise. Now we can superimpose in the PD signal the noise. Of course, the noise have a high amplitude in low frequencies, have a small level in the frequency of 1.2 megahertz, and high energy in other higher frequencies. For the reason, probably when we superimpose this kind of noise, probably the equipment that is working in a conventional method is probably, now we can see that it's impossible to measure with using this procedure. Now we can continue with this presentation in order to verify that this situation, sorry, in this case, we can increase the noise slightly, this kind of noise. And when we increase the noise, we can have on the right, on the left, we can see that the noise level is increasing and the PD pattern is losing. But on the right, we have the blue box technology. The blue box technology doesn't affect because blue box technology, based in well transformed mass statistic tools, remove the noise automatically and is not affected by the noise. We can continue. Of course, if we move the central frequency, measuring frequency, to measure in the instrument used on the left, for instance, in this case, if we move the central frequency that is up to 1.2 megahertz, you can see here, we can move the central frequency to 1.2 megahertz. In this case, we have the opportunity to recover the PD source, the PD pattern, because it's the frequency where the energy is lower. We can see the video. Now we have the opportunity to see again the PD pattern, because we have moved the central frequency of measuring central frequency to 1.2 megahertz. Of course, using the Wellet transformer, the Wellet technology, doesn't matter, it's not affected. It always can measure the PD source. But in this situation, we can change the noise. For instance, in this case, we have changed again the noise to other frequency, and we have to adjust the measuring instrument to other central frequency in order to measure. It means that if we use an instrumentation based on a Wellet transform, we don't need to touch, to select, to adjust anything. If we use another technology that is in the market, we need to select the frequency, to adjust the trigger, to carry out several settings that is not needed in this blue box technology, and this is the reason of the patent of this technology. Well,
thank you, Professor.
Yes?
You want to continue a little bit for the second
Yes.
section? Yeah, please.
Yes, it's only, I have to slide more and I finish. Well, in order to finish, we can use, with this technology, we can use different sensors. We can use the high frequency current transformer, that is the most interesting because we have a long range. Long range means very high scope to measure. We have around 2 kilometers of capabilities to measure partial discharge, because we are working in a frequency that emission is very small, and is working in the range of several kilohertz, tens, hundreds of kilohertz to 20 hertz. And we can use also other sensors like TEV sensor, or ultra high frequency sensor that are working in the frequency range around several hundred of megahertz or up to gigahertz. But in these cases, in these sensors, we have a shorter scope to measure, around several meters or several tenths of meters, no more. And depending on what kind of sensor can be used, we have more capabilities to measure partial discharge that appear very far. And of course, you can see in a substation, we have many capabilities to measure partial discharge in the transformer, in the GIS, in the cable, using the high frequency current transformer, because all partial discharge are traveling by the conductor of the cable, and this pulses is transmitted through the capacitance of the cable. For the reason we have the capability to measure using high frequency current sensors. Of course, we can measure also with TEV sensors placed in different places of the transformer, in different places of the GIS, in the spaces of the GIS. For instance, we can use this kind of sensor, or we can use ultra high frequency sensors invasive in the GIS, in the transformer, or in the windows of the GIS. You have here the small presentation of the different examples of different sensors. Sensor 1 is placed in a window. It's a high frequency sensor placed in a window. Sensor 2 is the figure and the picture you can see is a TEV sensor placed in a spacer. Sensor 3 is, you can see in the figure, is a sensor, ultra high frequency sensor, invasive ultra high frequency sensor. Or you can see sensor, for instance, 4 is a high frequency current transformer. But using the sensor 4, you can have also the opportunity to measure similar than you can measure using other sensor, invasive or non-invasive. And for the reason we can adapt the blue box technology to each sensor, but in any case, it can be used the measurement using the high frequency current transformer. Well, you have here different pictures in order to know how is the best location of the sensor, depending that you are interested to measure, but in any case, you can measure complementary with different sensors. Okay, I think for me, this is the first part of the presentation, and I think it probably is the most important, most interesting is to stop and to receive the comments and questions that is related with this part.
Thank you, Professor Garnacho. We will hold the Q&A session for next one after the session of Javier. Now, Parlin will make some summary in our language. So, thank you for giving us the presentation for the first 3 sections. So now I give the time to Pak Parlin to give the summary in Bahasa.
Oke, terima kasih Pak. Selamat siang Bapak-Bapak, Ibu-Ibu sekalian. Saya coba buat summary dalam bahasa Indonesia untuk masing-masing slide yang diberikan atau dipresentasikan oleh Profesor Garnacho tadi. Yang pertama lebih kepada teori daripada PD itu. Jadi definisi PD adalah pelepasan muatan listrik secara lokal dan hanya terjadi sebagian di bagian isolasi di antara dua konduktor. Jadi terjadi electrical pulse atau denyut listrik di dalam isolasi dan ini terpancarkan keluar atau secara radiasi. Beberapa jenis PD di GIS antara lain protrusion, yaitu PD yang disebabkan oleh adanya tonjolan tajam di HP parts atau konduktor. Kemudian free moving particle, yaitu PD yang disebabkan oleh adanya partikel bebas di dalam kompartemen GIS. Surface defect, yaitu PD yang disebabkan oleh adanya cacat di permukaan bahan isolasi, misalnya kurang bersih, ada noda, cacat bawaan atau goresan, retakan kecil, dan lain-lain. Kemudian floating potensial di elektrod, adanya floating potensial di permukaan elektrod yang biasanya akibat baut yang kurang kencang atau mungkin ada rongga atau bubble. PD di GIS akan mengalir melalui konduktor dan grounding baik di GIS maupun UGC. Artinya PD yang ada di dalam kompartemen GIS akan terpancarkan keluar GIS melalui konduktor atau HP part maupun sistem pentanahan di gardu listrik. Sedangkan untuk slide yang kedua itu tentang PD sources di kabel. Beberapa contoh jenis PD di kabel itu ada internal PD, ya, yaitu PD yang terjadi di dalam isolasi. Itu biasanya akibat void atau cavity yang ada di dalam isolasi kabel. Kemudian ada external surface PD, yaitu PD yang terjadi di permukaan kabel. Biasanya di sekitar terminasi HP kabel. Di sebelah sini, ya. Kemudian ada external corona, yaitu PD yang terjadi di permukaan bushing atau sealing end. Misalnya di sini. Dia kegagalan isolasi udara. Dan ini tidak berpengaruh tadi dengan partial discharge yang ada di dalam equipment, baik itu GIS, kabel maupun trafo. Jadi PD yang di kabel juga akan merambat melalui grounding. Kemudian sumber PD di trafo ada beberapa, misalnya di bushing, di winding, kemudian di tank, ya ini. Dan seluruh jenis PD ini akan merambat juga melalui grounding trafo. Sehingga kesimpulan dari apa yang kita bahas hari ini, bahwa PD di GIS, HV kabel maupun trafo akan merambat mengalir melalui pentanahan grounding. Yang menjadi masalah besar adalah bahwa akan terlalu banyak dan bercampurnya signal-signal di grounding, termasuk juga noise. Bahkan sering noise sangat tinggi, sehingga menjadi penting untuk mempunyai tools atau peralatan yang dapat mengetahui jenis dan sumber PD, memisahkannya dan membedakannya dengan noise maupun signal lainnya. Dengan menempatkan sensor di kabel GIS, sumber PD dapat dideteksi apakah berasal dari trafo, GIS, atau kabel. Blue box teknologi adalah sebuah alat yang bisa mendeteksi PD secara otomatis. Pada saat pengujian PD di lapangan, sinyal noise akan sangat banyak dan bervariasi. Solusi yang ditawarkan oleh blue box teknologi adalah noise suppression atau penghilangan noise berbasis pengolahan matematika menggunakan full sensor bandwidth. Tadi sudah dijelaskan oleh Profesor Garnacho. Tidak memerlukan filter frekuensi maupun level trigger dan tidak ada blind area, dan untuk pemantauan terus-menerus tidak ada masalah jika noise berubah-ubah. Dengan teknologi ini, PD pulse dapat dipisahkan dari noise maupun signal-signal yang lain. Signal berwarna biru merepresentasikan noise dan high signal secara real. Signal berwarna hijau merepresentasikan signal-signal yang ditangkap oleh sensor yang dipasang, baik itu HFCT, TFW maupun internal sensor. Signal berwarna merah adalah signal PD pulse. Jadi ini ada signal PD pulse di sini yang dia tangkap dan dia terjemahkan langsung dalam bentuk sinusoidal. Bentuk PD pulse dapat dilokalisir dan diperbesar dalam bentuk sinusoidal untuk mengetahui pola PD yang terjadi. Dari pola-pola tersebut akan diketahui sumber penyebab terjadinya PD. Nah, ini adalah untuk menunjukkan atau membedakan teknologi yang sesuai standar IEC 60270, yaitu konvensional method, dengan technical standard IEC 62, technical specification IEC 62478. Tadi Profesor Garnacho ada menyampaikan video tentang perbandingan antara percobaan untuk IEC 60270 dengan TS IEC 62478. Jadi pada pengukuran menggunakan IEC 60270, pengukuran pola PD sangat dipengaruhi oleh adanya noise, sehingga harus dilakukan beberapa adjustment. Tadi sudah kita lihat di video bersama-sama bahwa pada saat 1200 kHz, noise itu mempunyai sisi paling lemah, sehingga di situ baru bisa ketahuan atau dapat adanya PD. Baru bisa terlihat pada saat 1200 kHz. Sehingga perlu dilakukan beberapa adjustment untuk melihat pola PD yang ada atau yang terjadi di equipment. Sedangkan pada pengukuran menggunakan teknologi blue box yang mengadaptasi technical specification IEC 62478 dengan menggunakan mathematical noise suppression, pengaturan atau adjustment ini tidak perlu lagi dilakukan. Kira-kira seperti itu. Oh, ini tadi ya, ada tipe sensor. Tipe sensor ada 3 jenis, yaitu HFCT, TFV, dan invasif. Invasif ini adalah UHF sensor yang biasa sudah terpasang di dalam equipment, baik itu GIS maupun trafo. Jadi masing-masing punya karakteristik yang berbeda-beda. Saya rasa ini pun nanti akan bisa kita bahas lebih lanjut, bahwa HFCT itu skopnya bisa cukup jauh sampai 2 km. Sedangkan TEV itu hanya 5 sampai 10 meter. Sedangkan yang UHF itu sekitar 2 sampai 3 meter saja. Sehingga mempunyai beberapa keuntungan dan kelemahan. Jadi kira-kira seperti itu Pak yang bisa saya summary-kan untuk saat ini. Saya kembalikan ke Pak Victor. Terima kasih.
Terima kasih Pak Parlin. Bapak Ibu semua, harap bersabar. Jadi karena peserta dari webinar kami ini cukup bervariasi, ada dari kalangan akademisi, kemudian dari praktis, pelaku dari utility dan lain sebagainya. Jadi ini yang kami coba sampaikan, kami memberikan summary dalam bahasa Indonesia supaya bisa membantu kami paham dari survei yang kami lakukan. Peserta seminar kami tingkat pemahaman terhadap partial discharge cukup tersebar merata. Jadi harap bersabar bagi yang sudah lumayan expert. Kami mengcover di 3 section. Pertama adalah basicnya. Sekarang kita akan masuk ke bagian yang selanjutnya, section nomor 4 sampai 6, section 4 till 6 will be delivered by Javier Ortego from Madrid. Time is yours, Javier.